Hello students, today our topic is the relationship between uncertainty principle and the phenomena of diffraction. But before discussing the uncertainty principle, first we see what's the diffraction. For example, here we consider that the rays of plane wave front, which is along in this case along the vertical direction, are coming towards the slit AB. The size of the slit or opening of the slit AB is very greater than the wavelength of the light which is being used. The lambda is the wavelength of the light. Okay. After this case, we see that this ray as of light will fall here, and we will get the shadow of the slit AB here. It's a shadow of the slits. It's the normal case which we usually come across in our daily life. For example, when we see the shadow of the window, or we can say that in this case light rays don't change their original path, or they don't bend around the corner of the slits or edges of the slit, and they travel along the same direction in which already it was traveling. For example, we can consider it is along the x-axis. Okay. Okay, in this second case, the slits AB is the size of the slit is approaching to the wavelength of the light which is being used, and lambda is the wavelength of the light. When these plane wave fronts are coming towards the slit AB, after passing through this slit AB, they are no more straight, or the direction is not no more along the x-axis, but they spread or bent along the corner of the edges AB, and spread into the region beyond the slits where it should be no light, or where we should expect the complete shadow. But here we can see along with this blank band, we also can see the bright bands of light. Actually, we have already seen that in this case there should be the complete shadow of the slits AB, but here we cannot get the complete shadow, but the light has entered into the region where it should not actually enter, but it only occurs when the opening of the slits is comparable to the wavelength of the light which is being used. Now, before discussing the uncertainty principle, first we consider a beam of electrons having velocity Vy. They are moving along the y-axis, where m is the mass of each electron. Therefore, the momentum of the electron along the y-axis becomes my is equal to P is equal to this. Here we consider that the velocity of the electron is approaching to the velocity of the light. According to the de Broglie hypothesis, the wave is associated is this fast moving electron, and the wavelength of the wavelength of the wave which is associated with the moving electron is lambda in this case. Okay. Again, in this case, we consider a beam of electron which is coming along the y-axis. Therefore, the momentum Py is equal to this. But its component along the x-axis is 0. Therefore, in this case, we take that as we have already considered that the de Broglie wave is associated with the fast moving electrons. Therefore, these electrons can be, for example, if we consider a single electron, that it can be anywhere between A and B, because the wave spreads. The wave spreads, therefore this electron can be anywhere in between. In finding the exact location of the electron, there is an uncertainty, we cannot find the exact location of the electron, and the position of the electron can be anywhere between A and B. Therefore, the uncertainty in finding the position of the electron will be of the order of the length AB. Uncertainty means the error in finding the exact position of something. In this case, the uncertainty in the position means the error in finding the exact position of electron. Therefore, we can say that delta x is very greater than the wavelength, because this AB is along the x-axis. But there is no uncertainty in the momentum, or the uncertainty in the momentum is approaching to zero, because the total momentum of the moving electron is along the y-axis, and it has no component along the x-axis. Therefore, no uncertainty. Almost the uncertainty in finding the position along the momentum of the electron along the y-axis is approaching to the zero. And therefore, this electron will not spread around the corner of this slit, and they will move straight and fall on this screen, and we will get the shadow of the slit AB as in the case of the wave. Okay, and therefore, in this case, the electron is behaving like particles. Now consider the slit AB. Slit AB, the size of the slit AB is approximately equal to the wavelength of the light. Okay, as we have reduced the size of the slit AB, therefore we have reduced the uncertainty in finding the exact location of the electron. But on the other hand, it means, according to the uncertainty principle, the uncertainty in the momentum of the electron must increase. Because according to the uncertainty principle, the uncertainty in the position multiplied by uncertainty in the momentum along the same direction is greater than or is equal to the h over 2 pi. It means if the uncertainty reduces, the uncertainty in finding the exact momentum of the electron along the x-axis increases. It will be no more approaches to the light. Delta x is the uncertainty in the position, and delta p is the uncertainty in the momentum. Here this case. For example, now the electron passing through slit AB bent around the corner of the slits. The same case as it was in the case of wave, when the diffraction pattern we have seen occurred. In this case, the momentum P is no more along the y-axis, but there are two components of the momentum. One is the Py, which is along the y-axis. Another component of the momentum appears, which is along the x-axis. This momentum, which is the component of the momentum which is along the x-axis, is actually the uncertainty in the momentum has occurred. This delta px, actually the error in finding the exact momentum of the electron along the y-axis, because the actual momentum of the electron is along the y-axis, and it is the error in finding the exact momentum of the electron. Because we know that the momentum is a vector quantity, therefore these two components will add, and we will get this the resultant momentum. In this case, we can see that the momentums which are the particle, and due to the associated wave, the diffraction phenomena occurs, and they enters into the region where it should actually we cannot expect the presence of the electron, and again we get the same dark and bright, dark and bright band, dark band and bright band, as what is the case when we were using the light, and it was passing through the slits which was comparable to the wavelength of the light. In this case, again the electron which passing through the slits, the side of the slits is comparable to the wavelength of the wave which was associated with the moving electron according to the de Broglie, and we get the diffraction pattern, which is exactly according to the uncertainty principle. It means when we try to reduce the uncertainty in the position of electron, the uncertainty in the momentum of the electron increases. We have already seen that this uncertainty in the momentum of the electron was zero in the first case, but now it has increased. Now if we try to reduce it more, this delta px will increase further, and this beam of electron further spread into the region, in this region, and we will get more bright and dark bands. Okay, it means that this uncertainty principle actually explain the diffraction phenomena, and we can understand the diffraction phenomena with the help of this uncertainty principle. Okay, thanks.